So my co-author, Anne-Sophie, is also a participant on this program and wasn't able to come to the final workshop because she's teaching. However, she's listening to the streaming. So, hi, Anne-Sophie. So as I mentioned, Anne-Sophie was a participant on the program, and she was here for the first workshop back in July, and then went home a couple of weeks later to Quebec in Canada. And on the 28th of July, she gave a seminar. So it was one of the very first seminars in the program. And there she is up on Skype, actually. So Skyping in from Canada. And here we all are, looking very relaxed because it's the beginning of the program, unlike now, when we're not feeling so relaxed. And she talked for an hour or so about privacy for Bayesian modelling, and some of the people in the room were there. And afterwards we had a very nice discussion about, perhaps some of the concerns about differential privacy in particular, and what might be needed to sort of make it practical for statistical agencies to adopt. So then I hopped on my bike and I was happily cycling through the beautiful summer evening back up to West Cambridge. And I had an idea. I was cycling over there, why don't we try XYZ? So I was terribly excited, and the next day I called up Anne-Sophie and I said, I had this idea after your seminar, and something that we might try, and I don't know what's going to happen. But she also got very excited about it, and so what I'm going to tell you about today is the outcome of that journey, and it was a little bit of a journey. So it's all to do with the challenge of making data and analytical outputs available for research. So national statistical agencies, health data linkage units, and many other organisations around the world want to make their data available for research, get the benefits. But of course we've got these objectives, so we need to protect confidentiality for people represented in the data and preserve statistical usefulness. Traditionally we've thought of those as a trade-off. I prefer to think of a balance. I don't know that we automatically have to trade off. Let's think about balance. I also want to admit, I guess, or acknowledge in the context of this program, that I'm really looking at a very tiny slice of the problem of protecting confidentiality and making data available. So there are several frameworks out there. This decision-making framework is one of them, and there's many other factors that one needs to consider, and I'm just going to be looking at the one that's involved with the data itself. Okay, so if you're going to balance confidentiality protection and statistical usefulness, and sometimes these are called disclosure risk and data utility or utility, you're going to need some measures to help you do that. Okay, so you've got to, traditionally with confidentiality protection, we've focused on re-identification risk, and it's been an involved discussion of scenarios and intruders and situations. And about 10 years or so ago, the notion of differential privacy came along, which gave actually a formal definition for confidentiality protection. And that's been a huge step forward in the field. At the same time, we're also developing measures then for statistical usefulness in terms of, well, I guess what you'd really like, so you want your outputs of your analysis to be useful, even if they protect confidentiality at the same time. So you could think about perhaps you want your estimates to be accurate, you want your inferences to be correct. We've got a bunch of proxy measures for these things, but it's kind of hard to get really at the core of usefulness, except perhaps some of the tightness of confidence interval type measures around true values. I think they're starting to get close to real measures for statistical usefulness. Okay, so I mentioned differential privacy. So informally, differential privacy is a property of an analysis type or an analysis on a data set. And the idea is that if removing or adding an individual from the data set doesn't change the answer of the analysis very much, then it would be hard to learn too much about the person that you've added or removed. Okay? If there's not much difference between those two outcomes, you don't learn very much, and that's a confidentiality protection measure. And I think that's a very attractive and persuasive way to think about confidentiality protection. And of course, the individual that you add could be anybody in the population, so that there's a protection across the population for operating on this data set. Okay. So differential privacy is fantastic advance, as I mentioned. The clear definition and strong guarantees, I think, is inspiring everyone to think more in those terms about giving clear definitions, strong guarantees. It's had a massive impact on the literature, but a bit less in practice. Okay, we're not seeing differentially private methods and algorithms proliferating in these agencies that are trying to solve this problem. And the published concerns include, well, firstly, your definition doesn't actually mention statistical usefulness. Okay, so we've just got a definition that addresses the confidentiality protection half. But if it's a balance, then yeah, the usefulness is missing out of that definition. And people believe that the guarantees may be so strong that statistical usefulness may be unacceptably low. It's not always true. So there are some queries where you can get very good close answers with differential privacy, no problem at all, but others where people are struggling to find mechanisms that achieve that goal. So the research community has been proposing a range of relaxations that you can think of as exploring weakening a confidentiality guarantee in exchange for increased statistical usefulness. Okay, just kind of exploring that boundary, and we're going to propose such a relaxation. It's a little bit different in nature from the other ones that have been proposed, and I'll talk more about that as we go along. Okay, so I do need a little bit of notation. Hopefully it's suggestive enough that it's not too hard to remember. So D is a data set. You can think of it as a bunch of rows. Each row is an individual in the population. And two data sets are called neighbours if you get one from the other by just taking out a row or adding a row. Okay? Taking a row away or adding a row. U then, for universe, is all possible data set rows. And F is some sort of analysis on the data set with output F of D. And for the moment, I want that to be quite general. So it could be a count or a total or a table or parameters or even a synthetic data set. So any of those is fine. But I'll think normally about range as an element, a vector valued element with real numbers in the coefficients. So the idea then is to look for what are called randomized mechanisms, M for mechanism. That takes the function, applies it to the data set, and uses a random seed to introduce some randomness in order that you've got the differentially private property over the universe U. So I'll give you the formal definition that the randomized mechanism has differential privacy or satisfies differential privacy if for all neighbouring data sets with rows in U and all outputs this condition is satisfied. So what it really says is that the probability that the mechanism operating on each of the two neighbouring data sets is similar or the same, the probability is bounded. Okay, so it's just making formal that similar inputs give you similar outputs idea. Okay. And I want to speak about the Laplace mechanism. So this is an example of a differentially private mechanism. So we do need a little bit more definition. So the sensitivity of a function is the maximum difference between outputs of that function if operated on neighbouring data sets. Okay, so take two data sets that differ in one element, so you've taken in or you've put in or taken out one element, and calculate what's the maximum that the output of your function can change, and call that then the sensitivity. You can then define a mechanism that adds noise. Okay, so if you've got a vector valued function, you just want to add noise to each component, and the scale of the noise depends there on that sensitivity. Okay? Now this is a great mechanism for several reasons. One of which is that it's really very broadly applicable. So if we've got vector valued mechanisms, it's applicable, and also it's adding noise, which is a confidentiality protection approach that's been used for many years in the agencies. And so people are very comfortable with the approach of adding noise, and also statisticians have developed methods for analysing noisy data sets. So we, in many situations, can undo noise addition and get the right inferences. But not always. Okay, there's one other quantity I just want to bring to your attention, and that's called the accuracy. So for any parameter, for a parameter gamma, I want to define the gamma accuracy as it's actually I want it to be the length of this interval. Okay, so we've got the formula which you can read. The probability that any coefficient, because that's the maximum coefficient of the output of the Laplace mechanism minus the true value, so this is the amount of noise that you add, the probability that that's less than or equal to this quantity is greater than or equal to gamma. So it's a lot like a confidence interval, even though I've explained it really badly. I'm sure you know what I mean. Okay, so I'm going to use accuracy then, and the nice thing, of course, is that accuracy there depends on sensitivity in the case of the Laplace mechanism. Okay, so let's think then about the definitions that we've just seen for differential privacy. We've seen the Laplace mechanism. What are the things that perhaps make it difficult to use the Laplace mechanism or to get high accuracy? First of all, the universe may be unknown or largely unknown, so how would you compute the sensitivity over that universe? You might need to estimate it in some way, but even that may be difficult. So even if the universe is known, sensitivity can be very large, so your noise scale is very large, and that changes the values quite a bit. What the idea was, as I was, yes, Cynthia. Let me ask my question by example. So suppose each of us is just completely characterized by a binary vector of length d. Is the universe the set of all existing people, or is the universe the set of all strings of length d?
Actually, it's a really great question, Cynthia, because it's the one that I've been wanting to ask you.
So thank you. We can figure it out together. I mean, I've assumed that it doesn't actually matter if you choose one or the other, but what do you think?
Well, when you've defined everything in a strictly mathematical sense, we take it to mean the set of all possible strings.
Okay.
Of all strings.
Yeah.
If there is some externally known domain information, externally and publicly known domain information, then you can certainly say, hey, there's domain information that restricts the universe. For example, we know humans are not over 10 feet tall. We just don't have to worry about heights of that size. then it's completely fair game to say we're using the following known thing and therefore the universe is smaller. But I was
Yes.
wondering in your definition what you have in mind. But you don't, I mean,
Either one, I
since you
think,
want
is
to talk to me about
fine.
it, you can do that.
Yeah, we can do that afterward because I think either one works. You just have to interpret it slightly differently.
In the earlier in your slides, you said the universe were all possible rows of the data matrix.
Yes.
So that would be the rows instead of
What do you mean
the.
by possible rows?
Right, so
Yeah.
in your
It's
example, it
English
seems like
determined.
it wouldn't include anything larger than 10 in the column associated with height, maybe.
Only because we know that currently and
Right.
historically there haven't been people over 10 feet tall.
Right.
Yeah, but I believe that either works. But I guess I just wanted to focus on that idea that it may be unknown. But in contrast, everything about D is known. So the idea I had when I was riding my bike home was, oh, why don't you just use the bootstrap databases, which is the name then of the relaxation. But I've come to explain it in a slightly different way, so I'll tell you the way that we are talking about it in the paper. So we propose a relaxation that depends only on D. And so there's, I guess, a pictorial explanation where you know a lot about D and you know increasingly less and less and less about the rest of the universe. I'll come back to that idea as well. Okay, so the basic idea is that you don't mess with the condition of differential privacy at all. So most of the relaxations seek to relax that condition, but you mess with the scope. So instead of adding or removing a row or any row in the universe, you only add or subtract a row of the data set itself. Okay, so this is then has the effect of only having to look at the bootstrap databases. Okay, so we've just reduced the scope from the universe to D. And if you look at the privacy guarantees, they're reduced. Okay, so the arguments are the same. You've just exchanged the universe for the data set. So individuals in the data set have a reduced scope of claim of plausible deniability. They cannot claim to have any possible data value, but they can claim to have the same value as anyone else in the data set. Similarly, for individuals outside the data set, they're only protected for information leakage on joining a data set if they are the same as someone already in the data. Okay, so these are just adaptations of the plausibility arguments for the original differential privacy. And in particular, outliers that are not in the data set will not be protected from information leakage on joining. Now, I don't think it's better than differential privacy. I think the privacy guarantees are definitely weaker. But in some situations, it may be that those are not unacceptable. Okay, so let's go on. So I primed you to think that we were going to have a bootstrap Laplace mechanism, so we're going to have a bootstrap Laplace mechanism. Now, I haven't done a very good job with this slide because actually no, that's okay. It's all good. So the only thing that's changed is then the definition of bootstrap of sensitivity. It's now bootstrap sensitivity, and it depends on the data set D. Okay, so you only need to look at neighbouring data sets with rows in D, not rows in the whole universe. So generally, it's going to be smaller than the previous sensitivity. Generally, it's going to be known because your data set is known, although it may not be easy to compute. And generally, it's going to be bounded, which is also quite a nice property.
The bootstrap sensitivity in itself may be non-private. Leaking what the bootstrap sensitivity is may leak
Yes.
information about.
Yeah, that's right. Definitely. And you also find, you can compute obviously a gain in accuracy. I rather like the ratio because it shows you that the gain in accuracy is directly related to the ratio of the sensitivities, which which you would expect. Okay. So we decided to have a go at some tables, all right, because these are the workhorse of the statistical agencies. So we looked at, first of all, contingency tables. So these are tables of counts. And in the case of a cell count, the bootstrap sensitivity is equal to the sensitivity, because if you, it's better if I don't start explaining those because I get tangled up. Adding an individual adds a count of 1, unless a particular cell count is 0. So if you've got a cell described by certain characteristics in the population, then no matter how many people you swap in from the data set, no matter how many people you swap in from that data set, you're never going to get anything other than 0 there, because there isn't anyone with those properties. So zeros don't get perturbed. Zeros are not perturbed, and perhaps this corresponds to higher statistical usefulness for sparse contingency tables, because our structural zeros stay. But just thinking about it for a moment, adding individuals who are already in the data set will only change cell counts by 1 for people already in that data set. So individuals will only be protected amongst the individuals in the same cell. That's a weaker confidentiality protection. So for the contingency tables, you're going to get the same thing under bootstrap differential privacy as that you do under differential privacy, except that your 0 cells are not perturbed. So your zeros will be...
On the other hand, you are perturbing cells to 0. So this sort of random zeros are now protecting perhaps the ones that you're not
the zeros. Yeah. But we also looked at the magnitude tables. So let's imagine we've got a table of totals. And for a cell total, the bootstrap sensitivity is the maximum absolute value in that cell. Because if you're swapping people from the data set into the data set, you can only ever add totals that are already in the cell. Okay, so the maximum absolute value gives you the sensitivity, and again, for the same argument, 0 cells are not perturbed. The perturbations on the non-zero cells vary according to the maximum value of the data in the cell, the maximum value of the totals in the cell. And a larger maximum value in a cell gives you greater noise scale and lower accuracy. So once again, arguably, you might get higher statistical usefulness, in particular for sparse contingency tables, and you will get less, you won't get more noise. You may get less, and individuals, again, are only protected amongst the individuals in the same cell. So I'll show you then an example. It's some data about rice farms in India, and here we've got a two-way classification. So we're classifying the farms by variety and status, each with 3 levels. N is the number of farms in each cell. The net output is NOUT, and max is the maximum output for any farm in that cell. So in particular, just notice that there's some rather large value cells, so high owner and trad owner, and one nice little low one here. We chose epsilon equals 0.5 and applied Laplace noise independently on the cells. They're all non-zero, so okay. We did 10,000 replications because the Laplace noise is random, so we wanted to get the box plots. And in addition, we estimated the maximum output of any, for the purposes of differential privacy, you need to have a sensitivity for the population. So we just took the maximum value on the data as the maximum value on the population. So we didn't assume that there was any farms out there that were doing had bigger production than the ones we were seeing in the data. so as a bit of a conservative estimate. Okay, so there's a couple of things to notice. One is, of course, the blue is the differential privacy and the orange is the bootstrap differential privacy. So the differentially private estimates all have the same noise added, so they all look kind of the same, whereas the bootstrap differentially private estimates have noise that's calibrated by the size of the cell. And hopefully, yeah, there's less values have gone negative as well under the bootstrap differential privacy than under the differential privacy. Yes, so I think I've popped those into a little slide there. We also calculated the accuracy gain, so that was that ratio. Turns out to be algebraically the ratio of the difference between the sensitivities, and as I was showing earlier, that's the very small cells, so you're getting a lot more accuracy on the small cell and less on the larger cells. Okay, I'll talk a little bit. So this was as I mentioned, it was a bit of a journey, and of course halfway along we realised, well, why would you use the data set or the whole universe? You could actually choose anything in between that satisfied your need for confidentiality protection. So there's actually a nested family of populations that you could use as your scope for that condition in your definition of differential privacy, and the corresponding protection amount and accuracy should also be nested, so you can actually kind of use that as a way to trade off your protection and accuracy. And then we said, well, don't stop there. You know, we often think about Richard Branson or Bill Gates and what happens if they get added to a data set. Well, you know, we could make up a fake person and add them to the data set if we wanted to protect somebody, a sort of person in particular that we had in mind. Why not add them to the data set? And then under bootstrap differential privacy, the data set will protect against that synthetic individual. So one could go completely crazy and see what other mechanisms look like under bootstrap differential privacy and other variants like epsilon delta. So you can actually start to breed relaxations, and this is already starting to happen in the literature. And finally, something that is kind of our next investigation is how can you actually use the bootstrap distribution in differential privacy itself? And interestingly, that has already come up today as an idea to get a handle, because the bootstrap distribution is a good estimator often of the whole population, then that can help us to estimate some of those quantities that might otherwise be difficult to estimate. So I guess in summary then, we've had a lot of fun, and we've been thinking about this other notion of messing with the scope of differential privacy rather than the actual condition, and talked about bootstrap differential privacy. So it depends only on the data, not on the unknown population. One of the stronger points of it, let's say, is that there is still a clear description of the confidentiality protection guarantee, and that's not always true for some of the other relaxations. Sometimes it's quite hard to understand what is actually the protection. With this one, you can say, well, if you look like someone in the population, then you're okay, and if you don't, you might be in trouble. Yeah, we get an accuracy gain under the plus mechanism. So there's certainly weaker protections. However, perhaps they're sufficient in some situations when perhaps large or outlying values are unlikely to occur. But of course, in that case, differential privacy works well too. And perhaps also, interestingly, that protection level can be tailored to the situation and also tailored to the required accuracy. So I left plenty of time for questions, and hopefully Anne-Sophie is going to join us for the questions. I just need a moment. Thank you.
Could you put the definition one back up?
Oh, sure. Maybe. That one?
No. Yes.
Are we going to be able to see Anne Sophie on the screen?
Only when I switch it.
No, I'm sorry, I need the new definition of sensitivity.
Ah, right.
Thank you.
Okay, let's start. Well, Joseph had his hand up first, yeah?
Well,
Yeah.
yes. I like the presentation.
Thank you.
And it is maybe telepathy, but we represent something that is more or less the same tomorrow.
Oh, fantastic.
It's not completely the same.
Not completely the same, but very similar.
Yeah, I wondered about that when I saw your abstract. Yeah, ideas are evolutions, right? Here we go. Maybe I've got you upside down. Why isn't this working? There we go. Can you hear us, Anne-Sophie?
Yeah.
Ah, great. Can we hear you? Oh,
Yeah.
that's not working. We're going to have to look at you here.
Window cross.
How do I drag the window across? Oh, yeah. To which way, though?
Up, down, left, right.
Um,
It might be in full screen mode.
can you? All right, it is in full screen mode.
Continue with the questions. Yossi has a question?
So you said that this is weak. You said
Yes.
that this is weakening of differential privacy. So I'm not saying anything you didn't say. So an example where you may have problem is, suppose you look at the group of people in Cambridge who have a certain disease. They are all very similar to each other, maybe in the measurements taken because of the disease. Now you want to know if a particular person here belongs to that group or not. So he may be very different, and you will be able to identify, for example, that he does not, or does, things like this. So in this sense, the protection could be much weaker.
Yes. Yes, if you don't look like someone in the data set, then there's no guarantees.
So much of the privacy issue is to know whether a person belongs to a group or not.
Yep.
So if you don't look like somebody in the data set, consider the neighboring data set as the original one plus you.
Yep.
Your privacy in that neighboring data set is no longer protected.
Yes.
So, okay. Let me speak philosophically on behalf of the outliers. The average people don't need protection. It's the outliers who need protection. And this was an important part in our choice of the definition, specifically to protect everybody, including the outliers. I could imagine a situation where you have placed people into bins, a large number of bins, and most of the bins are very heavily populated and some of the bins are lightly populated. And then you'll have a certain amount of actual differential privacy protection under your definition, up to groups whose size starts to look like the size of the smallest bin. So that's a setting in which it makes some sense that you have outliers who are very rare, compared to the rest of the population, but you still have a substantial number of them. And in any database that you're likely to actually build, you're going to have a substantial number of them. But for these edge cases, I think it's troubling.
Did you hear that, Anne-Sophie?
Yes.
Okay, good. I guess what I would say with regards to that is that we're making here the assumption that you have seen a lot of the real data. Like if you have if you have a very small subset of the whole population, there might exist a lot of outliers that you've never seen. But if you imagine you have a larger piece of the data, or even like a census, right, then you've seen a lot of the possible outliers, and then you would be protected because you've seen them. So for sure, it doesn't protect in all the cases, and we never claim it was as strong as DC, but there might be circumstances where that is actually sufficient. That's what we had in mind here.
Yeah, that's right. I mean, I completely agree with your point, Cynthia. And indeed, we know that the protection is weaker, but in the spirit of kind of exploring options or perhaps situations where it might be appropriate. So I could imagine, we often talk about a person considering joining a data set. Okay, so they could actually look at the data set and say, oh, I do look like those kind of people, yeah, then it's okay.
How do they look at the data set
Yeah,
to make that determination?
I'm not quite sure, but I guess you often would know, maybe. You have a sense whether
You
you're
don't really have to be an
usual,
outlier
unusual.
person. You just have to be an outlier relative to the to the group which
I
is being
agree.
protected.
I
You
agree.
don't have to be crazy. You just have to be healthy, for example, and the group is sick people.
I think
That'll
the
make you stand
motivation
out.
here is like on a national database, like the census, so that's.
We were
That's where the
thinking
motivation
particularly
is.
about, national statistical agencies and
So it looks to me the only difference is that you, in this approach, is that you say we're not going to perturb the zeros, whereas in differential privacy we have to perturb the zeros.
well, it isn't the only difference. Yeah, the noise in the case of the plus noise will be less, tailored to the data.
Can I just ask what is the motivation for calling it bootstrap? Because, to me bootstrap means something completely.
Yeah, thanks for that question. We debated this as well because that was the original idea, but also it turns out that the set of databases that you have to consider, that you have to compute the sensitivity over, is exactly the set of bootstrap databases indeed.
So the empirical.
Yeah, it is actually that. And it's just a nice name.
Which points out that it's the non-parametric bootstrap. And the parametric bootstrap is like what you said when you added synthetic data. Rather than doing it haphazardly, you could do it via a parametric bootstrap, at least in principle.
And we did think about that a little bit. We haven't explored the idea very far yet, but we could imagine, instead of considering the non-parametric bootstrap, thinking about parametric bootstrap, and then you could sort of reach out to a little further potentially than the actually observed people in your data set. That's an idea we have. We haven't done anything with it yet.
Cool.
Any other
Agreed.
comments and questions?
I'd like to ask if the composition theory for differential privacy also holds here, and how does this play?
That's just asking about the composition theorems. Yeah, composition works for this variant because you're changing only the scope, not the condition. In fact, many of the theorems follow through if you remember just to change the scope. In the case that the data set is the whole, population, then it's the same. It's differential privacy, so it's just reducing the scope.
In a dynamic setting, you cannot do something that was not included in the data set, right?
Sorry?
In a dynamic setting, you cannot include a new record that which has a value that was not contained before.
Well, the protection would be less for that, than under differential privacy. Yes.
Any other questions? Okay, so let's thank you very much. Thank you, Anne-Sophie. 5 minutes extra for our coffee break. We're going to reconvene at 3:30. Then Cynthia Dwarf will have the final talk of the day at 4:15, and then we're going to have a women's roundtable event. But of course, everybody is invited, men and women, and after that, a wine reception. For those of you who are coming to the dinner tonight at Christ College, There is a map out there on the table in order to find the venue.